All right, good morning, everybody, and welcome to the final day of PLDI and to our third keynote session. I don't have too much to say today other than to remind folks that we do have the URM lunch today for folks that would like to attend that. And otherwise, just to thank all of you for coming to Copenhagen and coming to PLDI. You guys have all made this a fantastic event, and I look forward to seeing many of you in Seoul next year. And with that, I'm going to turn it over to John to introduce our final keynote speaker.
Yeah, I'd like to. We don't have any closing notes planned, so I'll just say now, so echo Millen's thanks to all of you for coming and being part of the event here. So I'm super excited to announce our third keynote talk this morning. It's Magnus Myrén. He is a professor at Chalmers in Sweden, and he's known for just sort of this broad and deep record of research on formal verification, and at the center of that, running through the center of his work is compiler verification, and we're going to hear about that today.
And thank you for giving me the opportunity to speak here. So compiler verification, first of all, let's get the motivation out of the way. Why do we want compiler verification? Well, I want it because I want to anything I prove about source level programs to transfer to the compiler generated machine code. Okay, so now that's out of the way, I want to actually start with a story. So the story involves an experience my PhD student Andreas Löw had. So he was working inside a theorem prover, or with a theorem prover, completely in the abstract. He had a verified KML. He had the verified KML compiler inside the theorem prover. He had proved that if you run it on his compilation of it on his verified custom CPU, that then he had on. And if you run that on an FPGA, it'll execute correctly. So he had worked months and really years on this, all within the theorem prover. And then one day, of course, he was ready. And then reality comes. Here's the FPGA. And OK, he ran this. He installed his implementation on the FPGA, and he set it running. Initially, it didn't do anything, but that's kind of expected because the compiler, while it runs, doesn't produce any output. It just sort of, in its default setting, just produces output at the end. And it took a while. He waited an hour. It's still not doing anything. And he's saying, like, OK, well, the CPU is really slow. It's very simple. The FPGA is clocked very slowly. So maybe it's just slow. But so he decided, I'm leaving for the day. And he went home, left it running. And he expected the next day, I'm going to spend all day debugging some completely incomprehensible error message. But no, it worked. So he turned up at work, and sometime while he was away, it had just produced the right output. And he was completely shocked by this, and that led him to write this in his thesis. An amazing story. And this is, someone who has devoted 5 years to formal verification. And he was still amazed by this, that it actually worked. And I have had similar experiences, so I'm really happy that he had this experience. You might ask, though, was Andreas lucky? Did it just happen to work? This is a complex thing he ran there, and this is the first thing he ran on it. Was he really lucky? And to answer that, I just want to show you what sort of is involved when doing these kind of proofs. So all of this in the yellow box is inside an interactive theorem prover. There he has the ML compiler, the CPU he's designed, he has his Verilog compiler, and all of these are connected via proof. At the top, he has a top-level specification, and at the bottom, he has a model of the FPGA that he's running on. So this is very much an end-to-end proof. But then there's the real intentions, and at the bottom we have the real physical FPGA. And if Andreas was something he should worry about, it's really these. Because did his real intentions really reflect in the top-level specification? That maybe is somewhat easier to deal with, but this is where I'd worry a lot. Did he really does the real physical FPGA work exactly like his model of FPGAs? So that's, to answer the question, was he lucky? Partly yes, maybe, that he got this right, but no, he shouldn't have worried about that. But still, there's something about it that is sort of shocking when you see it work, because when you're doing unverified code, it's this kind of complexity. It doesn't work. So then that leads on to the next question. Why did Andreas run the setup during development like any normal person? Well, to answer that, I want to explain a bit what a verified compiler often is. In the simple, it's like this. It's a function from source to output, and you have a correctness theorem. For example, it might say, for every input source program, the output program only has behaviors allowed by the source program, as a standard compiler correctness theorem. In reality, though, it looks a bit like this. You have a source program, and then you have tons of compilers that it has to pass through to get your output program. And during development, it actually looks like this. You have various components that are ready and verified and all that, implemented and verified. And as you go along, you insert these verified bits. And once you come to completion, you have both an implementation and a verification for all of it at the same time. So that means when you run it, it works immediately, modulo sort of specification bugs that you might have had. And so that's why you sort of, once it's done, ready to run, it's also already proved. And I have to agree with Andreas, it sometimes feels like magic because it's irrationally, I know that no detail was missed, but it's still surprising when you see it that it actually works. So then, okay, suppose you're new to compiler verification and want to get involved because to get this amazing feeling. Well, then you might go and look around what is in the sort of field of compiler verification. Well, if you do a Google search, you very quickly find CompCert, and you find a lot of projects around CompCert. And if you look a bit further, you might find KKML, which is a CompCert-like thing, but for functional languages. And then if you look even further, you find even more, and I'm sure I've left out tons of cool projects here, but you might still, if you're new to compiler verification, you might think, oh, is compiler verification an overcrowded research area? Because there seems to be a lot happening here, or has happened at least. And then my answer to that is definitely no. There's still plenty to do in compiler verification. So this talk, I'll talk about my experience in compiler verification. And as Oscar Wilde said, experience is all past mistakes. So I'll concentrate on sort of lessons learned as I went along, and also point out missing parts where I think it would be great to have contributions. So this is the sort of roadmap. Don't look at it too carefully now. We'll go through bits of it as we go along. So I'll start at my very first implementation of a verified compiler, or rather proof-producing compiler in this case. So to sort of back up, this is already at my PhD. My supervisor, Mike Gordon, said, can you try to verify some machine code? He had a very accurate model of ARM. And so this is the kind of thing I was looking at. How do I verify this? And then months later, to cut a long story short, I had a proof-producing decompiler, not a compiler yet. I'll show you what it does. So given some machine code, I mean, given the input on the left, the input, the right, the assembly on the right is just for readability. My decompiler produces a function, so we don't need to read the details of this, but you should see that machine code is it's literally just machine code that is given a semantics through an ISA model that is quite complicated. While this thing is very nice because you can read what it does. Here is an addition to register 0. Here's a memory load, and so forth. There's a loop, and so forth. So it produces a nice function for verification purposes. And then it also produces a proof stating that F accurately describes the execution of the machine code with respect to the ISA. So there's a connection. So anything you prove about this also talks about the machine code. And then came the idea like, Okay, but we could flip this around. We could make a compiler out of this. How do you do that? Well, the idea is very simple. It's very translation validation style idea. So to compile a function f, you generate without proof code from input f, no proof here, and then you run the decompiler you saw on the previous slide, and you get another function f prime. And then you just prove that f and f prime are the same for all inputs. And so you get your result because the proof this one produced is now about f. You can make it about f with that fact. So just to show you what it looks like from a user's perspective, the user has to write this. The compiler generates this and then gives you a proof that this indeed implements that. Just a note, because we'll see, I'll refer to this compiler later. Notice that to make this work, you, the user, have to do register allocation manually. And you have to write everything as tail recursive functions. It has to really have the feel of writing assembly without any compiler support. So maybe it's not really a compiler then, because it really is so direct. But the good thing about this, it's very quick to develop. And sort of as a PhD student, that's great. You want quick results. But it also fails seemingly on seemingly fine input because there's no guarantee that the tool will run to completion. And it's hard to explain. I understand what it should work on as input, but it's hard to explain to others. So if other people try to use it, it's a nightmare. But from my perspective, it's also nice because it has a flexible input language. Whatever I manage to program it to manage to prove, then it works for that. Okay, so I'm talking about verified compilers, but really there's a spectrum. There's verified compilers and there's proof-producing compilers. So these are proved to always work correctly, and these instead are proof-producing ones are producing a proof for each compilation run. And the compiler I just described is very much at that end of the spectrum. And I learned that it's brittle, it's unclear when it will work, but it was quick to produce, and that's handy, in fact. Just to get you a sense of what is on this side, well, you have, for instance, the famous composite C compiler is on this end of the spectrum, not at the very end, because it also uses some translation validation, so it's sort of drifted a little bit towards that, but it's definitely a verified compiler. Okay, so now I want to talk briefly about translation validation for taken to sort of the next level. After having worked on my decompiler, I worked on translation validation used by the SCL4 microkernel. So this is old, by the way. Now they're in 1 million lines, I think. So they really expanded that. When I sort of came to the project, they had this structure. They bottomed out at C code, and then they had low-level design, high-level design, and they had a refinement between them. But they trusted this C semantics they got through this translation from real C code into their model in the theorem prover. And the thing we wanted to do was extend this downwards and make this a not trusted arrow. So to do that, we run GCC as is, without any modifications, and then we need to connect this to that. To do it, we used my decompiler here, and that was quite robust and worked well enough. And then came the really hard part, that. Remember, previously we had the f is equal to f prime. Now this is a much harder problem, because here it has to sort of undo the compiler smarts. And this was work by Thomas Sewell, who did an amazing job of that, but still sort of coming back, sort of looking at it afterwards, it works for real code. So this is a great win. For GCC -01, the kernel hackers, they weren't happy with 01 though. They wanted 02 at least. But because 02 has so many tricks, the translation validation really struggled. You compile it once, then you update GCC even a little bit, and it doesn't work anymore because something changed. So it's very brittle implementation. And ever since this, so this of course lives also on the proof-producing compiler side. This made me think that, my impression is that this doesn't scale well enough this end of the spectrum. That's just my take-home message from this. We managed to get it to work on GCC, but that was a lot of work, and I don't recommend it. Okay, so next, all of my other projects are on this end. So I will talk about my first verified compiler. And the origin of this is actually during my PhD defense, Xavier Leroy asked, can your machine code Hoare logic reason about self-modifying code? And I hadn't actually verified any self-modifying code. But the way it was set up, it actually should be possible, and it was. And then I started thinking, what's the coolest application of self-modifying code? And I thought, OK, I'll do a verified just-in-time compiler. And that's how this came to be. So the implementation is, like before, like all of my programs so far, have always bottomed out at concrete bytes that are the machine code that runs the program. So the implementation that we verify is, or I verified, is a list of bytes that are the x86 machine code. And the specification we prove for this just-in-time compiler is that that code, when you give it a bytecode program to run, it will seem like an interpreter for the bytecode from the outside. But then internally, what it does is the implementation writes new x86 machine code into memory and jumps to them, and then occasionally calls back to generate some more code as needed. And yeah, that's how it works. One thing I want to point out that might not be obvious here is that the initial bytes that start off everything, it contains a code generator from bytecode to x86, because this is what it needs to do. When you give it a bytecode instruction, it needs to generate the x86 code for it so it can then jump and execute it. So here is an implementation of a code generator. And I didn't write this code generator implementation in x86 bytes. You know, that's completely nuts. Instead, I produced those bytes using my brittle proof-producing compiler from earlier. So here it came in very handy. And so you should know that there are two compilers involved here. There's that proof-producing compiler that compiled my bytecode to x86 compiler to have an implementation of it. Hope this is clear. This sometimes gets a bit confusing. So this was my first venture into this side of the space, and it was great. It's robust, it scales well, but of course it's inflexible because it proved once and for all. If I want to change the bytecode, I have to do a bunch of proofs and so forth. So positives, robust, clearly defined input language. It was fun to develop because it's one of these cases where it's just a blob of bytes, and it manages to do something as complex as run a just-in-time compiler, which is, it's one of these. When you run it, you're amazed that it actually works because there's so much that can go wrong when you're jumping to dynamically generated bytes. But it was completely toy, and it required a lot of ad hoc reasoning at the machine code level. So then comes the sort of next step, and the step just before the KML project. This exists because of an email from Jared Davis at UT Austin. Can you make a verified Lisp read-eval print loop that can run my Lisp theorem prover? And I thought, this sounds very interesting. And then I set off really scaling this up. And the new here was, it's a read-eval print loop. It has a GC, a verified GC inside it. So it was a big step from the previous one. And I learned that verified compilers really can scale, because running his theorem prover on a state-of-the-art Common Lisp takes 16 hours to start up his theorem prover. It has a very fancy startup sequence. So I also learned that the methodology works, but it's not perfect. In particular, I wish I didn't need 2 compilers, because at this point, compiling Lisp is not that hard, but but writing it so that in a style where you have to do the manual register allocation and write everything in tail recursive functions eventually really gets on my nerves. So we really wish we didn't need 2 compilers. And this is where the KKML project sort of, in some sense, got a start. So here, one of the things I wanted to address with the KKML project is that I wish we didn't need 2 compilers. And then this question comes, can we compile the KKML compiler with itself in the logic? So this is the big thing here. And now I'll explain how we got there. So first of all, there's this tool chain in the was from the very beginning of the KKML project. This tool chain was developed. It is if you give, I think there's an example. Yes, we have a tool chain. If you give the factorial function, which is a function in the logic, to this tool which synthesizes AST and is a proof producing tool, then you get an AST that has that behavior. You run it through the compiler. You get machine code that behaves exactly like the function you gave it. So what you get out is machine code that we have a theorem about saying that it behaves like the factorial function. So okay, now all we need to do bootstrapping is to have the compiler as a function in the logic. So we wrote a standard compiler than this one. This one can be seen as a compiler, but it has as its source functions in the logic of the theorem prover. So here we have a more normal compiler. It has a parser, type inferencer, and then compiler backend. And the important thing is that this is a function in the logic. If we insert that function in here, into this side of the tool chain, we get out the KKML compiler function as machine code. And hooray, it worked. We have, in the logic of a theorem prover, managed to arrive at the bytes that implement the KKML compiler. So this worked. Bootstrapping worked. Everything fits together. But it was really hopelessly toy in many ways, few optimizations at all. We went through a terrible bytecode in the process of compilation, which is very naive for performance reasons. So REPL demonstrates a use of bootstrapping, but the negatives are that a REPL is not useful for constructing verified applications, and we wanted to produce standalone applications that are verified using this toolchain. So in this read-eval print loop, we only had the I/O of the read-eval print loop to do any kind of I/O, so that is terrible for standalone applications. So here comes then the version 2. We gave up on the REPL, and then we went for, asked ourselves, how can we make this real? We wanted speed, we wanted better I/O, we wanted also a better methodology, and this is how the functional big step style came to be. And then we have the new compiler. Yes, it's much more advanced than the first one, which had like 3 or 4 stages only. This one has more than 30. And yeah, so I'll zoom in, but I'll go quite quickly here. So it starts off with parsing and type inference as before. It reduces language features in the beginning. It arrives at a language where it does OCaml-style optimization of multi-argument closures. Then it eventually goes to a first-order functional language, and then an imperative high-level language, so data abstraction still, called datalang. We'll come to datalang later. Then we have, eventually we remove the data abstraction. We arrive at machine types, and the rest is a sort of C compiler, but with a functional programming twist, because we have a garbage collector sort of appearing in the semantics and implementation. So we use a verified garbage collector that we inject in there. And we target multiple architectures at the bottom. So, and then we, of course, wanted speed as well. And this is slightly old, these performance numbers. But what I want to show with them is that we're comparing against native code compiled OCaml, Milton, SML New Jersey, PolyML, and KKML is the last one here. And what you should, don't read too much into exact details of this, but what you should take away from this is that the KKML compiler is in the same ballpark as the others. Sometimes it's faster, sometimes it's slightly embarrassingly slow, but it's in the same ballpark performance-wise. So we're happy with that. We didn't aim to be the fastest one. That's a bit over-ambitious when Milton's around. Okay, and then we're really happy that we could produce standalone applications because the SAT competition, this is just a picture of the SAT competition. This is not a performance of KML. The SAT solvers of the SAT competition are required to produce unsat proofs for every unsat result they claim. And the SAT competition then wants some way of checking that these unsat proofs are correct. So we're very happy that a verified KML compiled unsat checker is used by the unsat in the SAT proof competition to check these whenever a tool claims unsat. And now I have a slight aside. How do you verify manually written KML programs? Well, Arthur Shagorod's CFML is great, and we have an adapted version for KML that's proved sound with respect to the source semantics of KML. And then someone came to us and said, can you verify this code? Which is a kind of interesting little piece of code. It's a function that prints a y for yes, and then recurses. And yeah, this is just calling it so that it actually happens. Most programming logics can't prove this. And initially, ours couldn't either. But now we can because of these questions. And why is this problematic for program logic? It's because it doesn't terminate. And we have a total correctness logic. And it says, well, any judgment in it would have said that it terminates and this is the result, but here it doesn't terminate, so we couldn't prove it. But the result is that we have a new program logic on top of KML that can prove liveness properties for infinite runs, whether they are, so you can do it whether they're productive or not, because some frameworks that rely on co-induction require them to be productive, but ours doesn't. So what does this say? It says that the program, if you have this D on the post condition, it says that the program will diverge, and during its divergence, at the sort of limit, it will produce the infinite repetition of put string event, print an y. So this is what you want. It's a kind of total correctness version for infinite executions. LRepeat is just saying this will repeat forever. But there's a problem here, and now we get back to compiler verification. The compiler correctness theorem allows any KML program to exit early with an out-of-memory error. So this means if you prove that your source program for always will produce a y, then it might just terminate at some point once you've compiled it. So your liveness property didn't carry across. So this is sad. Our solution is that we devised a space cost semantics so that we can have liveness properties transfer from the source to the machine code. And the new alternative compiler correctness theorem is roughly like this. It says, if you manage to prove that the program is safe for space with respect to our sound cost semantics, then there's a strong equality between all the behaviors of the source semantics and the behaviors of the compiled program, including diverging behaviors. And there's no outer memory anywhere. So this means liveness properties proved at the source carry over to the machine code. And that's great. How do we then, so that's all very good. And we have then to actually use this, you have to prove that fact, that something doesn't go beyond what the space cost allows. But how do you prove it? That something stays safe. Well, there's an answer from Popple last year, but then, okay, it's a very nice development using Iris and so forth. Can you apply this for KKML's cost semantics? And the answer is no, not in its current form. There are many open questions on the way. And I'll explain a bit about the cost semantics. The cost semantics is specified at the level of data line. So this is good in a sense that it deals with all of this. So if you manage to prove something at that level, you get guarantees about the machine code that runs here, and you don't have to reason about the machine code, you don't have to reason about stack lang or word lang. You can be at a fairly abstract level of data lang, and you have a precise cost semantics. So the cost semantics is in slightly awkwardly defined as compilation down to data lang, and then apply the cost-aware operational semantics of data lang. This, from a user's perspective, is a terrible place to be, because you're reasoning about a compiler-generated code. So then the question, can we have a clean cost semantics for source-level KKML? And I say we don't know. And the reason is that, well, I think I have an example, yes. This is just a very simple example. Suppose you give this is standard ML syntax, this input to the KKML compiler. Well, you see a few things. This will be removed during compilation because it's dead code. And what you end up with data lang doesn't look exactly like this, but you could think of it as this. You get an allocation and then 3 conses. So allocations are bunched up. The CD assignment has vanished because it was dead code. And here, even in this really simple example, we see a few of the complicated things. Allocation doesn't happen at every cons. It's sort of shifted around. And because that's where the GC might run, it actually runs in a slightly different setting, because here we're taking the first element of F. If you were to have a cost semantics for this one, and this is considered an allocation, then it would need space. It would run allocate in a setting where the second part of F might not be reachable. So the GC could remove it. But here we move the allocation up, and so all of F is still live. And if you insert a function call here, it would be much worse. It couldn't move the allocation, and sort of it's hard to take a cost semantics from this and turn it into that and still have it be fairly precise without incorporating all the compiler optimization into the cost semantics, which is not what we want. We want something clean. So this is something that is sort of a missing part in our story, at least. So now I just want to get on a little bit with the rest of the KKML work. So I said that in the first we had a read-eval print loop, then we had no read-eval print loop, but we wanted the read-eval print loop again. Why is that? Because ML stands for meta language, which was originally developed for the LCF theorem prover. And working with KKML, we would like to apply KKML to a theorem prover to sort of close the loop. And that's what we really wanted to do. And this is where Thomas Sewell did an amazing job, presented at PLDI last year, to insert dynamic compilation into the KKML compiler. So this means now at the source language, you have an eval, a bit like Lisp eval, in your source, and you can dynamically, you could just call it with an AST for a program you want to run, and it will seem to be simulating it. But in reality, it compiles it to a machine code, inserts it into the running process, and jumps to it, and that's how it evaluates it. And remember I said that there was a lot of ad hoc reasoning at with my previous read-eval print loops and just-in-time compilers. That is completely removed now, because now you have this nice eval primitive in the source language. So you can write your entire read-eval print loop and all of that just as source program. But this was a major effort, but we're happy that it's there. This provides the E in the REPL. Now, zooming out, I want to sort of look at the KKML project a bit critically. So I'll try to give a sort of school report to the KKML project. let's start with the good grades. So a verified end-to-end compiler for standard ML or camel style language. That's tick, very good. And can be used to build verified applications, such as, for instance, the unsat proof checker, which is used. And we can even build verified REPLs, which is quite hard to do, I think, from my experience. If you can do it easily, great. And then we also get great marks for high-quality ITP code extraction mechanism. You might be familiar with Coq extraction, Coq's code extraction, but this is width proof all the way. So this is what I'm referring to is what I showed briefly in the bootstrap. You start with a function and logic, and you have a way of going all the way to machine code with proof inside the logic of the theorem prover. You don't have to trust the external world at all. Okay, so let's look at the intermediate grades then. Reasoning about space usage. It's great. We have a space cost semantics that is proved sound. The bad part is that it's really ugly to work with. And we don't have a good way of actually proving anything beyond small programs with it. So that's intermediate grade there. Then maybe a strange one here, marketing and communication. Maybe you think marketing is not important in research, but I think it is important to get the sort of word out. KML, of course, is fairly well known in verification circles, but at the same time, many people have got slightly the wrong impression about it. People say, oh, it's a standard ML program. It is standard ML, and because they're OCaml enthusiasts, they say, oh, that's not of interest to me. But I think this is very misleading because we actually use KML mostly through this pipeline, which concrete syntax doesn't come into the picture here. We go directly to an AST. And so it could equally well be OCaml, or it doesn't really matter. But this leads me on to onto the sort of bad grades. We invented a new programming language called KML, which is not exactly a subset of standard ML. It's not a subset of OCaml. It's our own thing. And I think this is like bad grades. And combine that with the next one, there's a lack of interoperability with other languages. And this then means that if you want to write some KML code, you have to write your entire program in KML. And this is very bad for adoption. So yeah, that's bad grades for that. And I hope there's a lot of room for improvement here. And now, with that said, I want to talk briefly about a sort of offshoot from the main KML project called PureCake. And here we really wanted to address one of the goals here is to address we invented a new language. And here, so PureCake accepts a subset of Haskell. And we really tried to be both syntactic, you can see the syntax of Haskell we can manage, and semantically the same. And we managed it quite well, I think, because a company called Cubic, who's behind the commercial use of QuickCheck, took our PureCake compiler and looked at the subset and wrote or adapted some Haskell code they had, several hundred lines of Haskell code to this subset, and then tested it against GHC compile. So PureCake versus GHC, and they found no semantic mismatches. We're happy about that, and we're surprised by that, actually, maybe. Okay, so in terms of performance, you'll ask about performance, surely. We are GHC 01, sort of thereabouts. So, and you might also say, well, the marketing here, why do you call it PureCake? It should be somehow verified Haskell or verified GHC. But I worry about that because that's really false advertising. We don't have type classes. How can you say this is Haskell? We're working on it, but to give the project the name, something GHC or Haskell, it's a bit, I think it's claiming too much. So that's why we stayed safe and pure for a pure language like Haskell, but a nod to KML because it builds on it. this is an actively developed compiler, so we hope to have type classes and everything later. And I just want to show you that just like the KML compiler, it also has a diagram like this. And different from the KML compiler, though, is that this one, instead of bottoming out at machine languages, bottoms out at the KML source code. So this is meant to compose, or this composes directly onto the KML compiler. You have pure cake source code, compiles through many stages down to, so this is call by value semantics. And then there's a bunch of optimizations of thunks to get down to KML source code, which then the KML compiler runs. And if you're a hacker for call by name, you'll say, well, if you use that as is, it's probably not going to be perfect for thunks. And well, we're addressing that. It's not yet addressed, but we are optimizing the KML GC for thunks. As I said, there's still much to do in compiler verification. Let me sort of recap some of the main points. I would claim there's not actually that many end-to-end verified compilers, so there's room here. And particularly, KML and Certicoq, I believe, are the only end-to-end verified compilers that use verified GCs. And this is kind of surprising because there's, of course, we use languages that use GCs all the time. So how come this, in terms of verified compilers, there's so few of them? So there's more very welcome here and more work here. And one of my big problems with this is that with compiler verification, at least the way I've been doing it, so I've been doing it wrong, is that it's easily all or nothing. Can we do something about this? So the current state is it's bad for adoption. And then, can we have more reusable parts? For instance, and a compiler project easily hard code nearly all proofs to the specific languages they're talking about. Because you want to do a liveness analysis on this, and then you talk about what it means to do liveness analysis on exactly that language, and every proof is tied up. There are certain parts that can be sort of algorithms that can be verified outside, for instance, naturally register coloring, the garbage collection sort of algorithm part, compilation of pattern matching, and so forth. But I think there should be even more reusable parts. There could be, for instance, if you have a language with these properties, then you can do an analysis like this. You can sort of instantiate an analysis rather than redoing the proof for that specific language. Now, of course, these are sort of high level, go and do this and everything will be great, but it's sort of hard to sort of size it. So I'm trying to give a few paper size suggestions here, and with that. So I think it would be great progress if we had formal specifications for major compilers, object file formats, and interface invariants, so that we have something to compile to. Currently, we have multiple ISA models to give us semantics of machine code, but to my knowledge, there's not very good specifications, at least in theorem provers, of the actual sort of interface you need to be composable with major compilers like OCaml and GHC. Once this exists, then we can talk about verified compilers that target these object files. And then comes the really hard one, verified separate compilation for functional languages. So anything to do with verified separate compilation tends to be very complicated, but it has really centered around compcert. So I think it would be really great if there was work on verified separate compilation for functional languages, really in a sort of end-to-end fashion where it really connects back to the actual interfaces that are used in reality, rather than some sort of mathematical, yes, this lambda calculus can talk to that. I want something much more concrete. I'm a very sort of practical sort of person. And then this is more to do with plugging holes of the cost semantics work that I think it would be really valuable and sort of to take the space cost reasoning from the Popple paper I referred to already earlier and use it on a cost semantics that's proved sound with respect to a compiler. So this, I think, it's just work, so to say. But it also could entail improving cost semantics, the phrasing of it, and so forth. Finally, finally of the paper-sized ones, I'm surprised, actually, that there hasn't been verified in-logic bootstrapping of an imperative compiler. So, for instance, why isn't CompCert C bootstrapped? I think it's, initially you might say that doesn't really fit, but I think it should be possible. Maybe not CompCert, but an imperative compiler should be possible, definitely. I think so. I haven't done it, but it should be. And then maybe PhD-sized suggestions, an end-to-end verified compiler that uses, or that compiles a language with reference counting. There has been work on verified reference counting, but sort of really getting the full story, full stack there would be great. And this is perhaps multiple PhDs. Rust is, of course, as we heard yesterday, a very interesting language. We should have a verified compiler for that. But that is maybe multiple PhDs. OK, so actually, before I show this, I just want to show that I've talked about all the projects I've been involved with. The first few projects were very just me working, basically, with maybe one collaborator. But the KCML project has really sort of been a very nice way of working with many, many people. The key developers are Ramana Kumar, Scott Owens, Jon Kian Tan, Andreas Lööv, Oscar Abrahamsson, Michael Norrish, Anthony Fox, Johannes Owen Pohjola. And then there's a lot of other people that have come and gone to the project. And this is, it's very nice to work on compilers because then you can, it's fairly modular actually. You have all these stages and you can sort of outsource one stage or new stage to a student, and as long as it fits into the proof, you don't need to worry about the quality. Well, you might worry about some of the proof style a complete new student might use. But in that sense, it's a great place to work with many people. But to my summary slide, I just want to say that from the KCML experience, I've learned that ambitious compiler verification projects are possible and very rewarding. But there's still much to be done. I particularly don't like the fact that currently, at least with the KCML compiler, it's an all or nothing choice, whether you use KCML or not. And just verified compilers should be easier to develop. And part of that is they should be more modular, have more reusable parts. Maybe there should be an archive of formal proofs, of compiler proofs that you can instantiate or something like that. And then surprisingly little work has been done on end-to-end verified compilation of memory-managed languages. And finally, my collaborator, very close collaborator, is looking for PhD students and postdocs. If you're into it or know someone, then get in touch. That's all.
So when I first learned functional programming as an undergraduate, the instructors warned us that there were a lot of misinformed skeptics out there who would say functional programming is only suited for writing compilers and theorem provers and not more general real-world stuff. And it was a really fun experience to learn standard ML. But as I've progressed through my career, mostly writing compilers and theorem provers, I've gotten more skeptical that maybe indeed at least the kind of compiler you've talked about is really only justified for domains like that have pretty complicated patterns of generating data and lifetimes of data. And it isn't clear to me it's worth the complexity of having functions represented as first-class values at runtime or garbage collectors. If you look at the great mass of code that's written in the real world, most of it isn't nearly complicated enough that you can't have a fully compile time understanding of those issues and optimize them all away. How do you think that might or might not that kind of observation might or might not motivate what kind of functional language compilers and runtime systems, etc., we should be thinking about verifying.
It is true that, yes, I agree, that functional languages are particularly good at pattern matching and then walking large tree data structures and so forth. And that is then compilers and sort of managing data. And it's very dynamic in the size of data. So if you meant for like the cost semantics work, should you go to that extreme? Maybe not. Maybe this is an academic exercise in trying to really make sure that we don't run out of memory. Because if you're really worried about running out of memory, you should be manually doing the memory management so that, or be in a language that gives you good control over that. So yes, that criticism is very valid. In terms of what KKML is useful for, I think the checker for unsat proofs is very good, because the correctness theorem there is saying that if this program says your input is good, it is good. Well, if it ran out of memory, it didn't say it's good, so it's still safe. You see, and it's useful for the community. So
does that example have complex allocation patterns that would be hard to manage at compile
yes.
time only? Okay.
Checking unsat proofs fast requires a lot of dynamic allocation. Yes.
Okay, thanks.
Great talk. So I have some question regarding bootstrapping C compiler, and I'm curious. I mean, there's of course Certicock project which has some motivation along that line, but I'm curious even for KKML and also maybe some HOL theorem provers, is there actually a result that shows you can truly produce standalone proof objects that remove the certified compiler from the TCB? I mean, I understand that different pieces that can be composed together, but it's
yes.
not a standalone proof object. But maybe I'm missing something there. So, like, define the problem. What do you mean by bootstrap?
Okay.
Yeah.
Bootstrap is, for me, in-logic bootstrapping is when you arrive at the machine code for the implementing your compiler, but you arrive at it using the compiler itself, all inside the logic. So, yeah, that's what I mean. So you have a theorem that just talks about bytes, and these bytes are implementing your compiler. Regarding the proof object part, this is not something I'm familiar with from the HOL world, because we don't have proof objects. Instead, in the LCF style, you prove a theorem, and then you prove the next theorem. You forget about how you proved it. You just, because it was developed, it was proved from another theorem object. So the theorem statement that you get at the end doesn't mention the compiler, other than, as in, you can produce standalone applications such as the unsat checker, and the theorem statement will not mention the compiler because it's been fully evaluated out to the bytes.
Right. So then in the code, it will be harder.
Possibly, as in, if you really don't want to mention the compiler in your proof object. Yeah.
I spend a decent amount of time interacting with the non-academic LLVM community, and those people are very good, and they have hard jobs. They're interacting with a multi-million line artifact that has a lot of optimizations. It supports a lot of targets, a lot of front ends. It's a hard job, and I struggle to see a way to get them to do the kinds of things you're doing. I think so. This doesn't mean I'm right? But this kind of makes me think that for these more industrial artifacts, that the translation validation side is probably more practical. But I'm always wrong about this kind of thing, and I wonder if just what are your thoughts on pushing the kind of techniques like you're talking about, or some variant of them, into industrial practice for real?
Yes. So that's why I started the talk with my motivation of I do compiler verification so that anything you prove about your source language goes down to the compiler-generated machine code. But there's another motivation you could have too, is that I want to improve unverified compilers using formal methods. And that also counts to me at some sort of compiler verification. And this is, I mean, I think the Alive project, for instance, is really doing this great. They're a big, so yeah, so that's one example of, but I haven't done that kind of work, so that's why I didn't talk about it. But I really suggest people read about the Alive work for that. And yeah, but I do agree with you that it would be good if we could sort of merge these somehow, so that, for instance, the LLVM compiler could have some phases that are actually verified compilers rather than some sort of translation validation based. Because I worry there are a lot of there are significant translation validation for the LLVM passes, but I think they're suffering from this brittleness, or I suspect so at least.
Yeah, you know, there are unfixed wrong code bugs, numerous unfixed wrong code bugs in the compiler, and same with GCC, and same with, I assume, every real compiler. And it's very sort of, you know, it's kind of distressing to as a computer scientist to work with these things that work like that. And you know, but of course this is the reality. The economic reality is that fixing those is expensive, and doing other things is
exactly
more worth people's time
or
something.
The research challenge is how can you make this cheap enough so that it's like it's routine rather than some academic exercise that takes a PhD to do.
Thanks.
So I was curious about the bootstrapping that you were talking about, because you're talking about bootstrapping, but just the compiler itself, so that the compiler compiles itself. But you have the logic on the other side, and if I understand correctly, for example, whole is also written in standard ML.
Yeah.
So do you think it's reasonable to try and verify whole with CakeML, like bootstrapping the logic part? Is that not so interesting, or is that much harder, and that's why you didn't address that?
So we have so the motivation for putting the REPL back into CakeML once we'd taken it out is that we wanted to have a verified whole prover. So we verified a clone of the whole light prover. So we have that. It's a soundness proof for it and all, and it's an end-to-end soundness proof. It talks about the machine code that's running, and it's doing dynamic compilation and all that. Cool. But if for you to really trust this, you have to realize that it came from whole 4, which is another prover that runs on an unverified compiler. So yeah, you haven't really removed it, like your dependence on some unverified compilers and all sorts of things. But as, for instance, John Roger's work shows, that verified compilers tend to be surprisingly robust, however empirically you sort of target them. So yes, you do depend on it, but I suspect it is very bulletproof, actually, the Candle compiler, which is our verified whole light.
Thanks.
So I'm sort of interested in the question of like how long it takes. I mean, or speeding up how long it takes to do like a proof of correctness for like a pass. And so like, I'm curious what kind of like bottlenecks do you see in sort of things that really absorb the most time when you're working on, you know, one of those proofs?
Well, one thing that strikes me when I have master students or something working on a new compiler pass is that they do their work and it takes a master thesis worth of, like, I don't know, 4 months, 5 months, which one of the more expert developers would maybe take a few weeks rather than months. But anyway, my point is that when they finish the master thesis, they say, okay, here's my pass, I can insert it into the compiler, and I end up doing the insertion into the compiler because there's a lot of sort of figuring out how it really fits in and all sorts of invariants that sort of need to be held across it, and that takes almost as much time as the sort of the idea of the optimization. So this is what I think. It would be interesting. It would be good if we could reduce that somehow. Yeah.
Thanks.
Thank you. I love the CakeML project. But I was wondering, you know, ML-like languages, like they're from the 80s or 70s. That's kind of from where I'm from, right? So what about, and garbage collection, by the way, is from the 1950s. So, and it's a kind of strange thing, isn't it? I mean, we got these compositional things, wonderfully composed, and then we've got this monster global thing called the heap and file system. That's like a huge global variable. And so you're saying like that's the hard problem. But these are not compositional problems. So what about parallelism? What about distributed systems? What about differential programming? There's a lot of approaches that should make it, in theory, easier to prove things because nice semantics and reasoning principles could be built into those, algebraic properties and so on. So what about parallel programming and languages and languages support differentiation and so on? Have you thoughts about how that could be profiting from, or the other way around, you profiting from KKML-like technology?
I'm afraid that goes beyond what I haven't. I've been so busy with all the sequential world and so forth, because there's so many problems there already, so I have hardly touched any parallel. But it would be interesting if there's something we could learn from that. In general, a parallel KKML or sort of with concurrency or something like that is, I think, very complicated. But yeah, if people do tackle it, if people are interested, because I think that's hard problems.
I mean, concretely, it would be nice to have some kind of GPU backends and
yes.
And as simple as possible, not concurrency and all those things, and try to attack that first. Thanks.
Yeah.
You mentioned the problem of modularity and reusability. Do you have an attack on how to solve that problem?
Well, we have attempted a little bit of that in the PureCake project, where we generally try to, do things better than in the KKML project. Sort of, KKML project is not so easy. Once you've settled on a methodology, it's hard to sort of try something new. But PureCake was one where we tried, and there we split the. We have different levels of expressions. For instance, where we have the semantic expression type, which is a fairly minimal thing that you write the semantics for and logical relation and so forth, all the reasoning you do at that level. And then you have the compiler expressions, we call them, which is the AST the compiler actually sees, and that de-sugars into the semantic expressions. That's one way, so that the compiler implementation gets a slightly richer AST that's sort of convenient to work with. And at the bottom, so this is one sort of detangling. Another one could be that various papers say, well, if you have this programming language, we are considering a programming language that has pattern matching and constructors and so it's enough to have pairs and the sum type. So theory papers say that, and then they go along and do everything with that. But real compilers want actual data types and so forth. So one could just do this as a sort of mapping into the sums and pairs, because it is possible. But then develop a way of doing these encodings very well, because the proofs then would be about the encodings, and the theory could be much neater underneath.
Thank you.
You mentioned in one of your answers that there are a lot of hidden invariants between the compiler passes, and that makes it subtle and hard to integrate. Do you think that's a fixable problem, and what do you think would help?
Yeah, this is, for instance, the problem is when we develop verified compilers, we very much obsess about the semantic preservation. But then there's occasional syntactic invariants, and these are the ones I talk about, that are they're sometimes hard to capture in the semantics, and those are the kind of properties we have to prove that syntactically a well-formed program becomes a well-formed syntactically well-formed program afterwards, because some pass further down, much further down, depends on this. So for instance, instruction selection happens quite early, and then it's only at the assembly stage where you have to know that you're how to combat that. some of it is maybe to have slightly better data types, but in a and some of it is putting it more into semantics where it maybe belongs, so that you don't have to prove many things over and over again.
Thank you.
We have time for maybe one more question. So I was going to say we have time for maybe one more question, but if not, let's thank Magnus for a fascinating talk and a lot of, I think, great ideas for future work. So the next sessions will start at 10:40.
Great.